Helium-3 is a light, non-radioactive isotope of helium with 2 protons and 1 neutron, in contrast with 2 neutrons in common helium. Its hypothetical existence was first proposed in 1934 by the Australian nuclear physicist Mark Oliphant while he was working at the University of Cambridge Cavendish laboratory. Oliphant had performed experiments in which fast deuterons collided with deuteron targets. Helium-3 was thought to be a radioactive isotope until helions were also found in samples of natural helium, which is mostly helium-4, taken both from the terrestrial atmosphere and from natural gas wells. Helium-3 occurs as a primordial nuclide, escaping from the Earth's crust into the atmosphere and into outer space over millions of years. Helium-3 is also thought to be a natural nucleogenic and cosmogenic nuclide, one produced when lithium is bombarded by natural neutrons. Those are released by spontaneous fission and by nuclear reactions with cosmic rays. Some of the helium-3 found in the terrestrial atmosphere is also a relic of atmospheric and underwater nuclear weapons testing. Most of this comes from the decay of tritium, which decays into helium-3 with a half-life of 12.3 years. Furthermore, some nuclear reactors periodically release some helium-3 and tritium into the atmosphere. The nuclear reactor disaster at Chernobyl released a huge amount of radioactive tritium into the atmosphere, and smaller accidents have caused smaller releases. Furthermore, significant amounts of tritium and helium-3 have been deliberately produced in National Arsenal nuclear reactors by the irradiation of lithium-6. The tritium is used to boost nuclear weapons, and some of this inevitably escapes during its production, transportation, and storage. Hence, helium-3 enters the atmosphere both through its direct release and through the radioactive decay of tritium. The abundance of helium-3 is thought to be greater on the Moon than on Earth, having been embedded in the upper layer of regolith by the solar wind over billions of years, though still lower in quantity than in the solar system's gas giants. Physical properties. Because of its lower atomic mass of 3.02 atomic mass units, helium-3 has some physical properties different from those of helium-4, with a mass of 4.00 atomic mass units. Because of the Wick-induced dipole-dipole interaction between helium atoms, their macroscopic physical properties are mainly determined by their zero-point energy. Also, the microscopic properties of helium-3 cause it to have a higher zero-point energy than helium-4. This implies that helium-3 can overcome dipole-dipole interactions with less thermal energy than helium-4 can. The quantum mechanical effects on helium-3 and helium-4 are significantly different because with 2 protons, 2 neutrons, and 2 electrons, helium-4 has an overall spin of 0, making it a boson, but with 1 fewer neutron, helium-3 has an overall spin of 1/2, making it a fermion. Helium-3 boils at 3.19 K compared with helium-4 at 4.23 K, and its critical point is also lower at 3.35 K, compared with helium-4 at 5.2 K. Helium-3 has less than 1/2 of the density when it is at its boiling point, 59 gram per liter, compared to the 125 gram per liter of helium-4, at a pressure of 1 atmosphere. Its latent heat of vaporization is also considerably lower at 0.026 kJ per mole compared with the 0.0829 kJ per mole of helium-4. Fusion reactions. 3He can be used in fusion reactions by either of the reactions 2D plus 3He 4He plus 1P plus 18.3 MeV, or 3He plus 3He 4He plus 2 1P plus 12.86 MeV. The conventional deuterium plus tritium fusion process produces energetic neutrons which render reactor components radioactive with activation products. The appeal of helium-3 fusion stems from the aneutronic nature of its reaction products. Helium-3 itself is non-radioactive. The lone high-energy byproduct, the proton, can be contained using electric and magnetic fields. The momentum energy of this proton will interact with the containing electromagnetic field, resulting in direct net electricity generation. Because of the higher Coulomb barrier, the temperatures required for 21H plus 32 He fusion are much higher than those of conventional DT fusion. Moreover, since both reactants need to be mixed together to fuse, reactions between nuclei of the same reactant will occur, and the DD reaction does produce a neutron. Reaction rates vary with temperature, but the D3 He reaction rate is never greater than 3.56 times the DD reaction rate. Therefore, fusion using D3 He fuel may produce a somewhat lower neutron flux than DT fusion, but is by no means clean, negating some of its main attraction. The second possibility, fusing 32 He with itself, requires even higher temperatures, and thus is even more difficult than the D3 He reaction. However, it does offer a possible reaction that produces no neutrons. The protons it produces possess charges and can be contained using electric and magnetic fields, which in turn results in direct electricity generation. 32 He plus 32 He fusion has been demonstrated in the laboratory and is thus theoretically feasible and would have immense advantages, but commercial viability is many years in the future. The amounts of helium-3 needed as a replacement for conventional fuels are substantial by comparison to amounts currently available. The total amount of energy produced in the 21H plus 32 He reaction is 18.4 MeV, which corresponds to some 493 megawatt-hours per 3 grams of cube T. If the total amount of energy could be converted to electrical power with 100% efficiency, it would correspond to about 30 minutes of output of a gigawatt electrical plant per mole of 3He. Thus, a year's production would require 52.5 kilograms of helium-3. The amount of fuel needed for large-scale applications can also be put in terms of total consumption. Electricity consumption by 107 million U.S. households in 2001 totaled 1,140 billion kWh. Again, assuming 100% conversion efficiency, 6.7 tons per year of helium-3 would be required for that segment of the energy demand of the United States. 15 to 20 tons per year given the more realistic end-to-end conversion efficiency. Neutron detection. Helium-3 is the most important isotope in instrumentation for neutron detection. It has a high absorption cross-section for thermal neutron beams and is used as a converter gas in neutron detectors. The neutron is converted through the nuclear reaction N plus 3 He 3H plus 1H plus 0.764 MeV into charged particles tritium and protium, which then are detected by creating a charge cloud in the stopping gas of a proportional counter or a Geiger-Müller tube. Furthermore, the absorption process is strongly spin-dependent, which allows a spin-polarized helium-3 volume to transmit neutrons with one spin component while absorbing the other. This effect is employed in neutron polarization analysis, a technique which probes for magnetic properties of matter. The United States Department of Homeland Security had hoped to deploy detectors to spot smuggled plutonium in shipping containers by their neutron emissions. But the worldwide shortage of helium-3 following the drawdown in nuclear weapons production since the Cold War has to some extent prevented this. As of 2012, DHS determined the commercial supply of boron-10 would support converting its neutron detection infrastructure to that technology. Cryogenics. A helium-3 refrigerator uses helium-3 to achieve temperatures of 0.2 to 0.3 kelvins. A dilution refrigerator uses a mixture of helium-3 and helium-4 to reach cryogenic temperatures as low as a few thousandths of a Kelvin. An important property of helium-3, which distinguishes it from the more common helium-4, is that its nucleus is a fermion since it contains an odd number of spin 1/2 particles. Helium-4 nuclei are bosons, containing an even number of spin 1/2 particles. This is a direct result of the addition rules for quantized angular momentum. At low temperatures, helium-4 undergoes a phase transition. A fraction of it enters a superfluid phase that can be roughly understood as a type of Bose-Einstein condensate. Such a mechanism is not available for helium-3 atoms, which are fermions. However, it was widely speculated that helium-3 could also become a superfluid at much lower temperatures, if the atoms formed into pairs analogous to Cooper pairs in the BCS theory of superconductivity. Each Cooper pair, having integer spin, can be thought of as a boson. During the 1970s, David Lee, Douglas Ocheroff and Robert Coleman Richardson discovered two-phase transitions along the melting curve, which were soon realized to be the two superfluid phases of helium-3. The transmission to a superfluid occurs at 2.491 millikelvins on the melting curve. They were awarded the 1996 Nobel Prize in Physics for their discovery. Tony Leggett won the 2003 Nobel Prize in Physics for his work on refining understanding of the superfluid phase of helium-3. In zero magnetic field, there are two distinct superfluid phases, a 3He, the A phase and the B phase. The B phase is the low-temperature, low-pressure phase which has an isotropic energy gap. The A phase is the higher temperature, higher pressure phase that is further stabilized by a magnetic field and has 2 point nodes in its gap. The presence of two phases is a clear indication that 3He is an unconventional superfluid, since the presence of two phases requires an additional symmetry, other than gauge symmetry, to be broken. In fact, it is a p-wave superfluid, with spin 1, s equals 1, and angular momentum 1, L equals 1. The ground state corresponds to total angular momentum 0, J equals S plus L equals 0. Excited states are possible with non-zero total angular momentum, J greater than 0, which are excited pair collective modes. Because of the extreme purity of superfluid 3He, these collective modes have been studied with much greater precision than in any other unconventional pairing system. Medical lung imaging. Helium-3 nuclei have an intrinsic nuclear spin of 1/2, and a relatively high magnetic ratio. Helium-3 can be hyperpolarized using non-equilibrium means such as spin exchange optical pumping. During this process, circularly polarized infrared laser light, tuned to the appropriate wavelength, is used to excite electrons in an alkali metal, such as cesium or rubidium, inside a sealed glass vessel. The angular momentum is transferred from the alkali metal electrons to the noble gas nuclei through collisions. In essence, this process effectively aligns the nuclear spins with the magnetic field in order to enhance the NMR signal. The hyperpolarized gas may then be stored at pressures of 10 atmospheres for up to 100 hours. Following inhalation, gas mixtures containing the hyperpolarized helium-3 gas can be imaged with an MRI scanner to produce anatomical and functional images of lung ventilation. This technique is also able to produce images of the airway tree, locate unventilated defects, measure the alveolar oxygen partial pressure, and measure the ventilation-perfusion ratio. This technique may be critical for the diagnosis and treatment management of chronic respiratory diseases such as chronic obstructive pulmonary disease, emphysema, cystic fibrosis, and asthma. Production. Current U.S. industrial consumption of helium-3 is approximately 60,000 liters per year. Cost at auction has typically been approximately $100 per liter, although increasing demand has raised prices to as much as $2,000 per liter in recent years. Helium-3 is naturally present in small quantities due to radioactive decay, but virtually all helium-3 used in industry is manufactured. Helium-3 is a product of tritium decay, and tritium can be produced through neutron bombardment of deuterium, lithium, boron, or nitrogen targets. Production of tritium in significant quantities requires the high neutron flux of a nuclear reactor. Breeding tritium with lithium-6 consumes the neutron, while breeding with lithium-7 produces a low-energy neutron as a replacement for the consumed fast neutron. Current supplies of helium-3 come, in part, from the dismantling of nuclear weapons where it accumulates. However, the need for warhead disassembly is diminishing. Consequently, tritium itself is in short supply, and the U.S. Department of Energy recently began producing it by the lithium irradiation method at the Tennessee Valley Authority's Watts Bar Nuclear Generating Station. Substantial quantities of tritium could also be extracted from the heavy water moderator in CANDU nuclear reactors. Production of helium-3 from tritium at a rate sufficient to meet world demand will require significant investment, as tritium must be produced at the same rate as helium-3, and approximately 18 times as much tritium must be maintained in storage as the amount of helium-3 produced annually by decay, T1/2, where the value of T1/2 is about 18 years, see radioactive decay. If commercial fusion reactors were to use helium-3 as a fuel, they would require tens of tons of helium-3 each year to produce a fraction of the world's power, requiring substantial expansion of facilities for tritium production and storage. Abundance. Solar nebula abundance. One early estimate of the primordial ratio of 3He to 4He in the solar nebula has been the measurement of their ratio in the atmosphere of Jupiter, measured by the mass spectrometer of the Galileo atmospheric entry probe. This ratio is about 1 to 10,000, or 100 parts of 3He per million parts of 4He. This is roughly the same ratio of the isotopes in lunar regolith, when it contains 28 ppm helium-4 and 2.8 ppb helium-3. However, terrestrial ratios of the isotopes are lower by a factor of 100. Mainly due to enrichment of helium-4 stocks in the mantle by billions of years of alpha decay from uranium and thorium. Terrestrial abundance. 3He is a primordial substance in the Earth's mantle, considered to have become entrapped within the Earth during planetary formation. The ratio of 3He to 4He within the Earth's crust and mantle is less than that for assumptions of solar disk composition as obtained from meteorite and lunar samples, with terrestrial materials generally containing lower 3He, 4He ratios due to ingrowth of 4He from radioactive decay. 3He has a cosmological ratio of 300 atoms per million atoms of 4He, leading to the assumption that the original ratio of these primordial gases in the mantle was around 200 to 300 ppm when Earth was formed. A lot of 4He was generated by alpha particle decay of uranium and thorium, and now the mantle has only around 7% primordial helium, lowering the total 3He, 4He ratio to around 20 ppm. Ratios of 3He, 4He in excess of atmospheric are indicative of a contribution of 3He from the mantle. Crustal sources are dominated by the 4He, which is produced by the decay of radioactive elements in the crust and mantle. The ratio of helium-3 to helium-4 in natural earthbound sources varies greatly. Samples of the lithium or spodumene from Edison Mine, South Dakota were found to contain 12 parts of helium-3 to a million parts of helium-4. Samples from other mines showed 2 parts per million. Helium is also present as up to 7% of some natural gas sources, and large sources have over 0.5%. The fraction of 3He and helium separated from natural gas in the U.S. was found to range from 70 to 242 parts per billion. Hence the US 2002 stockpile of 1 billion normal M3 would have contained about 12 to 43 kilograms of helium-3. According to one expert, about 26 cubic meters or almost 5 kilograms of 3He is available annually for separation from the US natural gas stream. If the process of separating out the 3He could employ as feedstock the liquefied helium typically used to transport and store bulk quantities. Estimates for the incremental energy cost range from $34 to $300 per liter NTP, excluding the cost of infrastructure and equipment. Algeria's annual gas production is assumed to contain 100 million normal cubic meters, and this would contain between 7 and 24 cubic meters of helium-3, assuming a similar 3He fraction. 3He is also present in the Earth's atmosphere. The natural abundance of 3He in naturally occurring helium gas is 1.38 times 10⁻⁶. The partial pressure of helium in the Earth's atmosphere is about 0.52 pascals, and thus helium accounts for 5.2 parts per million of the total pressure in the Earth's atmosphere, and 3He thus accounts for 7.2 parts per trillion of the atmosphere. Since the atmosphere of the Earth has a mass of about 5.14 times 10^15 tons, the mass of 3He in the Earth's atmosphere is the product of these numbers, or about 37,000 tons of 3He. 3He is produced on Earth from three sources: lithium spallation, cosmic rays, and beta decay of tritium. The contribution from cosmic rays is negligible within all except the oldest regolith materials, and lithium spallation reactions are a lesser contributor than the production of 4He by alpha particle emissions. The total amount of helium-3 in the mantle may be in the range of 0.1-1 million tons. However, most of the mantle is not directly accessible. Some helium-3 leaks up through deep-sourced hotspot volcanoes such as those of the Hawaiian Islands, but only 300 grams per year is emitted to the atmosphere. Mid-ocean ridges emit another 3 kg per year. Around subduction zones, various sources produce helium-3 in natural gas deposits which possibly contain 1,000 tons of helium-3. Wittenberg estimated that United States crustal natural gas sources may have only half a ton total. Wittenberg cited Anderson's estimate of another 1,200 metric tons in interplanetary dust particles on the ocean floors. In the 1994 study, extracting helium-3 from these sources consumes more energy than fusion would release.